Hi, everybody. We're going to do section 1.5. It's going to be a pretty short but sweet. Well, definitely short, hopefully sweet. And it's on summation notation and some generalizations of it. And this section is really going to be more just teaching you different notations. I'm not going to do that much in this section other than show you notation. And a lot of it you probably know already. So let's go. I'm gonna get rid of my personal video because it's hard to explain. It just interferes a little bit with me. So here we go. So sums. So summation notation, which you've probably all seen at a certain extent, um, in a finite series, is expressions such as a1 plus a2 plus a3 dot 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 plus an. So you write that as the sum. This giant symbol here is a Greek letter sigma, capital sigma, and k is the variable that kind of moves, or the index they call it, and it goes from 1 through n. So when k equals 1 of ak. So when k equals 1, you have a1. When k equals 2, you have a2. When k equals 3, you have a3. All the way up to k equaling n, you have an, and then you add them all up. That's why do you add them all up? Because that's a summation symbol. If that was a giant capital pi, then that would be the symbol for product. Then this thing would be a1 times a2 times a3 times dot 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 times an, but it's not. It's a sum. Anyway, so in this expression here, let me highlight it. Oh no, I can't. No, it doesn't seem to be letting me do that. If I could do it this way. No, it's not letting me do it. Okay, sorry. I wanted to highlight, but it's giving me a. Maybe I can highlight this one. Sometimes it just ain't working. Anyway, so the variable k is called the index. The expression ak is called the general term of the series, and it defines the numbers which are being added together in the series. Okay, but what's the difference in a series and a sequence? A series is when you have the pluses. A sequence is when you have commas. So 1, 2, 3, 4, that's a sequence. 1 plus 2 plus 3 plus 4, that's a series. These are just words. I'm just giving you the typical definitions. Anyway, the value of k below the summation symbol is the initial index, and the value and the one and above this is the terminal index, the one that's above the sigma. So in this example, 1 is the initial, 4 is the terminal. These are just terms and words that are commonly used. And it's understood that the series is a sum of the general terms where the index starts with the initial index. It increases by 1 up to and including the terminal index. So if you have the sum as I, so here I is the index, as I goes from 1 to 4 of AI. So when I is 1, it's A1. When I is 2, it's A2. When I is 3, it's A3. And when I gets to the terminal index, the terminal 4, then it's A4. And whatever these A1s happen to be, whatever these A1, A2, all that stuff happens to be. Here we see it's a sum from 0 to 5, so we'll go B0 plus B1, dot, 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 plus B5. Here you see it's going from -2 to +2, so it's C sub -2, C sub -1, C0, C1, C2. Just a little more, just some more slightly concrete examples. Here we have the sum as I goes from 1 to 4 of I squared. So the AI is the index number squared. So when I equals 1, I get 1, but I'm squaring it. When I equals 2, I get 2 squared. When I equals 3, I get 3 squared. When I equals 4, I get 4 squared. But it's a summation, so I'm going to add them all up. And it gives me 30, because that's 1 plus 4 plus 9 plus 16, which gives me 30. And here we have the sum as I goes from 1 to 5 of 2i minus 1. So again, it's 2 times 1 minus 1, and then plus 2 times 2 minus 1, plus 2 times 3 minus 1, plus 2 times 4 minus 1, plus 2 times 5 minus 1. If you notice, these numbers, this I can highlight. These are the ones that are changing. Everything else is sort of like the template. You know, the 2 and the times and the minus 1, that's sort of the template. And the only part of it that this is actually changing is the I which is the 1, 2, 3, 4, 5. Meanwhile, you add this all up, you get 1, 3, 5, 7, 9, you get 25. If you notice, this is really just a sum of odd numbers. 1, 3, and by the way, whenever you add up odd numbers, you always get a perfect square. I think you know that. In this manner. So moving on. Now we're going to generalize this concept to things other than sums. I mentioned earlier in this video that you can generalize it to products instead of sums, but also you could now we're moving on to generalizing this idea, this notation, to other things other than just sums. And we mentioned that you could generalize it to products. If you had a big pi symbol instead of a sigma symbol, that would mean the product of the various symbols. But now we're going to generalize it not just to numbers, but to sets. So we're going to generalize it to sets and operations on sets. So if you have the intersection of A1, A2, dot, 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 AN, you can write that as the intersection as I goes from 1 to N of AI. And that, so this and this is the same thing. Or if you have the union of a bunch of sets, you can write the union as I goes from 1 to N of AI. Now, all these things, we're gonna see these things used, but for section 1.5, we're just explaining the notation. All we're doing today is we're not doing any actual math. We're just in this video, we're just giving notation. This is the cross product of a bunch of sets. This would be ordered n tuples. This would be the symmetric differences of a bunch of sets, and so on and so forth. Let's look at some actual examples here. Suppose the set A1 set 1 is 023, and then set A2 is 1236, and set A3 is negative 1039. So if I want to say the intersection as I goes from 1 to 3 of AI, well, that's equal to A1 intersect A2 intersect A3, which means it's all the numbers that are in all three sets. And of course, there's only one number, which is the number 3, because 0 does not appear in the middle set, 2 does not appear in the end set. I mean, that's it. The only number that's in all three sets is a 3, 3, and 3. It's a 3. And that's intersection. I could also look at the union here. Union of, let me go back to, oops, let me scroll up a little bit, just so you can get the union is, I'll write it this way. Union is I goes from 1 to 3 of AI. So that's going to be AI union A1, union A2, union A3, those three sets, and subtracting all the duplications. You're not subtracting, but you don't, you just eliminate duplicates. So you get negative 1, 0, 1, 2, 3, 6, 9, because those are all the different numbers that appear in these three sets. And there you go. So we've used this notation, this summation type notation, for other things other than numbers. We use it for sets, and that's the way that goes. And summation notation can allow us often to make a bigger statement very compact. For example, if I take the intersection of set A with the union of all these B's, we this equals A intersect B1 union A intersect B2 union dot 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 union A intersect B, and that's a formula, famous formula in set theory. And here we have, I could rewrite this right now. I'm not doing the math right now. I'm just showing you the notation. I could rewrite this as A intersect. The union is I goes from 1 to N of BI, which is all that's what this whole thing here is. And that's equal to the union as I goes from 1 to N of A intersect BI, which is what I have here. A intersect B1, A intersect B2, da, 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 da. So again, this instead of writing this long thing here, I could write a much shorter thing like this. And that's why we have notation in general. That's really the whole point. The whole point of notation is to make things more that's weird. How do I get rid of this? More brief. How do I get rid of this? Okay. Anyway, that, my friends, is the story, and I'm sticking to it. And that's the end of section 1.5. See you guys next time. Bye.